Hello, everyone, and thank you for joining us today. I am your host, Shannon, and welcome to the webinar, Understanding Measurement Uncertainty for Electric Drives. Now, just a friendly reminder, all participants' microphones are muted during the webinar. Please do not forget to activate your PC speakers to enable audio or connect headphones to your PC. You may have to take the step of joining the audio conference to hear sound. Please type any questions you have into the WebEx Q&A dialog. You can open the Q&A window by selecting the Q&A icon in the WebEx toolbar at the top of your screen. Today's presentation will be emailed to all attendees. The webinar will also be posted on our website. If you have additional technical questions, feel free to contact our technical support team at support@usa.hbm.com. Now, I would like to present Alexander Stock. Alexander earned his master's in electrical engineering at the Technical University of Applied Sciences, Ashvenberg. I'm not going to try and pronounce that. And his doctorate in engineering focused on dynamic power measurements in electric motor drive applications. He recently joined HBK as a technologist focused on electric power testing. And when he's not in the lab, he enjoys traveling, endurance sports such as biking, jogging, and he enjoys cooking. I would now like to welcome Alexander to begin the presentation.
Yes, thank you for the kind introduction, Shannon. Good afternoon. Welcome everybody to this presentation about understanding measurement uncertainty for electric drives. First of all, I want to give you an overview of the content of this presentation. At the beginning, I will start with challenges if we are measuring on the electric drivetrain. I will then move on and link to the measurement uncertainty. We will discuss what this is, measurement uncertainty, why we want to know about it, why it's so important to reduce it, and all those things. Furthermore, we will have a look how measurement uncertainty in measured quantities propagates to other quantities which are calculated from these measurands. And in this context, we will especially have a look on the measurement uncertainty of electric power in dynamic measurements. Finally, I will also present a hardware circuit which can be used to verify measurement uncertainty of dynamic measurements. This is a development project in cooperation with the university in Aschaffenburg. And I will conclude with a short summary and an outlook. So, as just mentioned, for the beginning, we want to have a look on the electric drivetrain. Here you can see a typical example how such a drivetrain could look like. We have the electrical machine, we have an inverter, which is used to transfer energy from a power source to the machine, or in generator mode, vice versa. And we have in the center of this graphic, we have a data acquisition system, in this case, Genesis 4TB, and this system is used to measure all the relevant physical quantities we are interested in. And the system could furthermore be connected to, for example, a measurement PC. The measurement PC could be used to analyze data or also to set up the measurement settings in the measurement system. And of course, the measurement system could also be connected to an automation PC, which is kind of a supervising control unit. The automation PC could, for example, be used to define set point values for the inverter control in order to drive to the next relevant operating point. And the first important question is, what signals should be measured in this electric drivetrain? This is, of course, on the one hand side, if you think about electric vehicle applications, we have a battery, therefore we want to measure the DC signals at the output of the battery. DC signals, of course, in reality, we will also see there some transients depending if operating points are changing or not. And we can also see some reflections from the inverter so that we have high frequency components in it, but in the ideal case, these were DC signals. In addition to that, we want to measure typically the output signals of the power inverter, which are the input currents of the machine as well. And we have in this case here a three-phase machine. And in order, for example, to be able to calculate the efficiency of such a machine, it's necessary to measure, in addition, the mechanical quantities, torque and speed, which then define, of course, mechanical power. And beside these electrical quantities, It's often of interest to measure temperatures, for example, the winding temperatures of a machine, or also of the inverter and the battery. And a lot of customers are also interested in vibration measurements and also in acoustic noise signals. And a big challenge is to collect and store all these signals, all these different physical quantities, time synchronously, and the raw data sample by sample in order to be flexible and to be able to calculate further parameters, system parameters, relevant quantities, everything the customers are interested in. And if we talk about challenges, I want to show you another challenge, and therefore I distinguish between two different types of electric drives. On the one hand side, we have often quasi-stationary drives, which are operated, as the name says, most of the time in steady-state operating points. This is the case if we think about typical industrial applications such as pumps or fans, for example. And these drives are characterized by the fact that the signals, if we take a look now at the inverter output in this plot here on the top, then you can see that during steady state conditions for constant torque and speed, also the electrical signals are in a steady state, which means they are periodic signals. Of course, the voltage contains the harmonics of the frequency inverter. And if you would zoom in the current, then we would also see a current ripple, which includes switching frequency harmonics of the inverter. But nevertheless, these signals are nice periodic signals. And therefore, if we are interested in values such as active power, apparent power, reactive power, all power quantities, RMS values, but also fundamental quantities, then we can apply the well-known laws which are part of the standards. All of them are based on detecting the fundamental cycle of those periodic signals and then do evaluations based on this cycle. But if we go now to a lot of modern highly dynamic drives, for example, if we think about automotive applications or robotics, then these drives are characterized by the fact that they are typically not operated in one or only a few steady-state operating points. They are typically highly dynamic, which means frequency as well as amplitude may change frequently or even continuously, and we do not have steady-state operating points. And we have here on the bottom a picture of a startup process of such a machine. It's a no-load startup. This means we only need torque to accelerate the machine, and therefore torque producing currents, which you can see over here. But you can also directly see that these are not periodic signals or non-periodic signals. And of course, you can do a zero crossing detection in order to detect or calculate an apparent fundamental cycle. But as we all know, a fundamental cycle is only defined for periodic signals. So of course, we can do evaluations as we do it for the steady-state operated drives, but it may also lead to some misinterpretations. But what we can always do is we can calculate instantaneous values, such as instantaneous power, sample by sample. That's the reason why we need that and why it's so important to measure raw data, because then we can use the instantaneous power to investigate balancing processes, transients, or even subharmonics, which come from mechanical oscillations, all those things. And what we can also provide, this is also a part of a development in cooperation with Aschaffenburg University. We developed a highly dynamic power analysis method, which can also be used to analyze those signals. And it is not linked to the fundamental cycle of the signals, it's linked to the switching cycle of the inverter. And therefore, the power quantities can be calculated with a drastically increased update rate. That's a big advantage, but that only as a side remark so far, because today the most important topic is measurement uncertainty. That's the reason, after having discussed some challenges in measuring the drivetrain, I want now take the gap and go to the measurement uncertainty. Therefore, in order to dig into that topic, I will start with some statements which define what measurement uncertainty is. I will start with a statement from the guidance of uncertainty in measurements. So it's not really standard, it's a guidance, but it's the basic procedure or the basic document which describes procedure of evaluating measurement uncertainty. And it says, in general, the result of a measurement is only an approximation or estimate of the value of the measurand, and thus is complete only when accompanied by a statement of the uncertainty of that estimate. That is, of course, true, but of course also very detailed, and we can sum that up or summarize that. And there is a professor, Professor Werner Richter from Leipzig University in Germany. He said specifying a measurement result without indicating the measurement uncertainty is so uncertain that it is better not to specify it at all. Or if we even summarize again and we directly hit it to the point, then Dave Packard said measurements are always wrong. It's just a matter of how wrong. So all of those are true, and we will now try to make these statements in words a bit more technical. And for this, in the first step, I want to show you, based on an example, why measurement uncertainty is such an interesting and important topic. Therefore, we start again with the measured quantities. As we just heard, all measured quantities contain a certain amount of measurement uncertainty. That's related to the fact that measurement processes are also influenced by environmental effects and conditions, and the environmental conditions can often be not controlled or not infinitely accurate controlled. And in addition to that, all measurement equipment, independent from the manufacturer, each sensor, each power meter, contains a lot of different components, and all have manufacturing tolerances. And independent from the level of quality, it is impossible to build up a really absolutely perfect system. And for those two reasons, each measured quantity contains measurement uncertainty. And if we now think again about our electric drivetrain, we measure voltage and current. Both of the measurands contain measurement uncertainty. And then we calculate energy, power, or efficiency from these measured quantities. And of course, the measurement uncertainty of the measured data propagates to the calculated data. And if we go now a step further to our vehicle application, then the vehicle, of course, one part of the vehicle is the battery with a defined and limited battery or energy capacity. And if we calculate the energy consumption of the car from our measurements, and we have measurement uncertainty in that energy consumption, then also the expected range of the car has a kind of measurement uncertainty. Or in other words, if we have a lower measurement uncertainty in voltage and current, this enables a higher range specification of our vehicle. And that is one example why a lot of our customers are so interested in this topic. Now, to go to the analysis and how to evaluate measurement uncertainty, I want to again distinguish between different error effects. In this context, I distinguish between two groups: systematic error effects on the one hand side, and these errors are characterized by the fact that they are reproducible if I repeat a measurement in the first step equal environmental conditions, but also, of course, with the same operating point. And then, since we can reproduce by following measurements these error effects, they are generally avoidable by compensation. And if we talk about measurement, this means calibration. And examples are, only to mention some environmental conditions which are not compensated for, such as temperature. Temperature affects, for example, the input amplifier, because resistances in the input amplifier are temperature dependent, for example. Or again, the manufacturing tolerances of passive components. And we have here a nice metaphoric picture, the target with bow and arrow. So if you imagine the side of the bow is mounted in the wrong angle, then you can shoot the arrow as often as you want. You will never hit the center target. And that is a typical systematic error. And on the other side, we have random error effects. And these random error effects lead to measured values which scatter around the true value. And this is also the fact if we compensate the systematic errors and if we have the same ambient conditions, or let's say apparently the same ambient conditions. These errors are therefore unfortunately not reproducible, and we cannot compensate for it. And we can, in this group, again distinguish between kind of a, let's call it real randomness, which is related to quantum mechanical processes such as thermal noise or resistive noise. And we have, that is also an important one, apparently random, but actually deterministic processes. And they are characterized by the fact that the origin is unknown and they seem to be random. But in reality, of course, you could explain it by classical physics, but the model is too complex. If you think about our error again, for example, continuously changing wind conditions could be such an error because wind, weather, and also turbulences are deterministically chaotic processes. You can explain them by classical physics, but it's too complicated sometimes, and therefore a very small change in the ambient conditions leads to a very different measurement result. That's what characteristic for chaotic processes. And as you realize from this explanation, it's sometimes difficult to group the errors in one of these two groups, to separate it. And it's also possible that if we have an apparently random effect, that this may be transferred to a systematic error effect if we improve our model of the measurement process and then are able to explain the behavior and then also able to compensate for it. So this is not always absolutely separated, but it's important to treat it different. And with these two different kinds of errors, we want to talk about some other basic terms. So if we do a measurement, we typically do not know the true value. That's the reason why we measure. And if we then in the first step consider that we only have systematic errors and we measure and we do the measurement again and again and again, the measured value will, due to systematic errors, not be equal to the true value here, but it could be, for example, here. But if we're talking about systematic errors, for each measurement, the result would be here. But this is not what we know from real measurements. If we measure several times after another, then we will see that, of course, a lot or most of our measurements are very close to this expected value. But there are also some which are a bit more far away. And this is related to random errors. And we can model this by probability distributions. This is the red curve. In this case, as an example, it's a standard normal distribution. And the probability distribution defines the probability that the measured value is in a certain interval around the expected value. So for a standard normal distribution, round about 68% of the measurements are in an interval of minus to plus the standard deviation around the expected value. And if you would not have any systematic errors, which is not possible what in the last detail, but of course by calibration you can nearly achieve that, then the expected value is equal to the true value. And with this knowledge, we can now go to the error propagation, which means we measure some quantities and then we calculate others from these measured quantities. And if we know the error of the measured ones, how does that propagate to the calculated ones? And I added during the next slides, for reasons of completeness, a bit more information as it is possible to explain here in this limited time frame of a webinar. But for reasons of completeness, if you read through it after the presentation, then you are able to see also the details, the mathematical details. But I will try to explain only the main information which you need from that slide now in this presentation. So if we talk about error propagation, and we want to calculate the maximum error of a variable y, which is a function of other variables, in this case then measurands, x1, x2, and so on. So let's imagine y would be the power. Then, of course, the power is a function of voltage and current. So x1 could be the voltage, x2 the current. And then the question is, how big is the maximum error in the power if we know the errors of voltage and current? And then you can see that for the maximum error, we sum up the absolute error influences. I call it error influences because it's not only the error, it's the error multiplied with a sensitivity coefficient, with this, which is the partial derivative, but that's not too important so far. The most important is we sum up the absolute value of these individual error influences. And if we talk about typical measurement uncertainty, that means we are talking about random errors. And we know, for example, the probability distribution and the standard deviation of those variables. Then we can do the error propagation with the Gaussian error propagation formula. And as you can see in the result, this is not the sum of the absolute values, but it is kind of a squared sum or geometric sum. And this is if you would insert the same values as for the above one here, then this leads, of course, to a smaller value. And that gets clear if you think about the fact that systematic errors are always fixed, but the random errors can be for one measurement, one value is a bit too high. For the next one, the value is a bit too low. And this is also for the different quantities. One quantity may be a bit too high, the other one a bit lower. And then at the end, errors can cancel out. And for this reason, we do it with the Gaussian error propagation. And we can now use these formulas to apply that on the active power. In this easy example, the DC active power, which is well known as the product of the DC voltage and the DC current. And if you now apply on that formula the Gaussian error propagation, then you will see as a result that the relative measurement uncertainty of active power is equal to the squared sum of the relative measurement uncertainty of the voltage and the relative measurement uncertainty of the current. And you can also do that for the easy example of sinusoidal AC quantities, so ideal sinusoidal AC quantities. Then, of course, the phase shift between voltage and current is also here included in the formula. But this is, of course, nice and important, and it's also useful to do this in the first step, because if you think about electric drive applications, the electric machine represents a high inductive load. Therefore, the currents are more or less sinusoidal, as we saw in the measurements before. And for this reason, most of the active power is transferred in the fundamental. And if you know the measurement uncertainty of the fundamental, that's a good estimate to guess how big the overall measurement uncertainty of the total power could be. But of course, if you want to go into detail, we need something different. And this is what we want to achieve with this, the measurement uncertainty of power measurement for arbitrary waveforms. And for this, we would have to start at the point that the active power is defined as average of the instantaneous power over the fundamental period. But of course, this is a mathematical analytical challenge to do that in general for all arbitrary waveforms. But what is done on the measurement system, if we look how it is calculated over there, this is the discrete representation of an average. And what is done is for each sample time, we measure voltage and current, we multiply that. This gives you the instantaneous power value of this sample. And then we sum up over n samples and divide by the number of n, which is then again the average. Of course, n depends on the ratio of sample frequency to fundamental frequency if we link the averaging to the fundamental cycle of the electric signals. But it can also be a timed average. So this is not restricted in this formula. It's only a mean value. And for this, we can again easily apply the Gaussian error propagation, which leads to this button formula. And this one is now again a suitable method to estimate or calculate measurement uncertainty of active power for arbitrary waveforms. What is important here to state as well is that this formula does so far not contain bandwidth effects, so sensors which are of course limited in bandwidth somewhere, and also filter properties, for example. But it's possible to consider this in addition as well. And now we see that we have also for dynamic signals a measurement uncertainty propagation formula. But now the question is, what are the main challenges by evaluating this? And therefore, it's obvious that each individual active power value is calculated from a number of n samples of voltage and current. And each of these voltage and current samples then again contains an amount of measurement uncertainty, which propagates to the active power. And this measurement uncertainty of each sample contains then some systematic errors and some random errors. Systematic error is, again, if you think about the manufacturing tolerance, perhaps a capacitor or resistance in the input amplifier of the data acquisition system is a bit too big or too small, and therefore the scaling or the offset is influenced, then this error is the same or influences the measurement result on this individual channel for each sample in the same way. And therefore, it cannot be compensated by increasing the number of samples we use for averaging. That's typical for systematic errors. We cannot make them smaller by increasing the number of samples which we use for averaging. On the other side, we have random errors, such as noise, for example. And if you think about noise, this is not the same from sample to sample. For one instant in time, it can be a bit too big. For the next instant in time, it is a bit too small. And therefore, it may cancel out each other from sample to sample. And for this, these errors may be reduced by increasing the averaging interval. That's also the reason why a lot of people who need high accuracy, they do not average the active power over only one fundamental cycle. They take a multiple integer of it. And as you can see from all those things, it is really important, if you read through the data sheets, that the interpretation and the categorization of error influences is really important. It's one of the bases. And we can take a closer look here again. So if we take, for example, only one quantity, the current, then the current measurement, in order to measure the current, we have a lot of different sensors in the measuring chain. For example, the current transducer, over here, the burden resistor, and the input amplifier, or the power card in this case. And all of them, contain measurement uncertainty, and of course, in addition to the environmental conditions. And so what we should do is we need to calculate the measurement uncertainty of all of those components, and then each component, if you look into the data sheets of those components, each component is specified with different influencing effects. If I say influencing effects, I talk about things like temperature depending errors, aging dependent errors, nonlinearity error, or Earth's magnetic field influence, and all those things. And if we now have the different influencing effects of all those components, these may again be specified in different ways. Some of them are absolute values, which means for currents perhaps several microamps or milliamps, and others are specified relatively with respect to measuring value or measuring range. And some of them are specified in a combination of both or all three. And no, all three, not both. And the total measurement uncertainty is then, of course, a result of the superposition of all this information. And for DC and AC, this can be quite, or not too difficult, but it starts to get complicated also there. And of course, it is really difficult if you do that then for dynamic signals. And what we are doing at the moment, we are developing a tool who does that for our customers, the measurement uncertainty tool. And here you can see a screenshot of the first prototype version of this measurement uncertainty tool. If you take a look on it, and if you remember the beginning of the presentation, we had the battery, which of course is kind of a DC power. We have the inverter output, which is kind of an AC power, and we have the electric machine with a mechanical power. And what you then do in this tool is you specify the hardware which you used for your measurement. So the module, the current transducers, the torque transducers, how speed is measured. Then you specify, of course, important the ambient conditions, such as the ambient temperature interval, min and max temperature, the time which is elapsed since last calibration, all those side effects. And then you can calculate the measurement uncertainty. And what you get as a result is you get the specified power, which you measure, the power range, and also the measurement uncertainty as absolute and also as relative information. And of course, this is a first step to do that offline for steady state operating points. But you can imagine the long-term goal is that we specify that with the measured value. And this is a really nice method to do that. And it, of course, makes it much easier for the customers because, as you saw from the slides before, it is really quite a lot of effort to do that manually, hand by hand, going through all the data sheets. And it is often difficult to categorize what is a systematic, what is a random error, and all those things. And now, in order to verify all those results, again, in cooperation with the university in Aschaffenburg, they developed a circuit, which is in principle two completely galvanically isolated full bridges. But these isolated or galvanically separated full bridges are controlled with a PWM, which is synchronized, which means that we have for one full bridge a very, very precise DC voltage source. For the other one, the current source. And we can use the full bridge here with the silicon carbide semiconductors to generate more or less ideal rectangular output signals here in the output. So AC signals. And if you imagine that the PWM is synchronized, so this means the rectangular output signals are synchronized, then if I would calculate, I call it a virtual DC power because the power is nowhere in reality because the two measurement circuits are galvanically isolated, but we can calculate a power from the DC signals. And if we then do also a power calculation from the AC signals, this should deliver exactly the same result if we do not have measurement uncertainty in our AC measurement. And you can see that if we take a look on some measurement examples. These examples now have been measured with an oscilloscope in order to show how good the rectangular waveform is. You see the scale here, the rise time is approximately 50 nanoseconds. So this is very suitable to compare power meter with sampling frequencies in a range from 1 megahertz to 10 megahertz. And since the DC power is for almost all sensors and power meters specified in a very precisely, then the deviation of DC and AC measurement in combination with the DC specification gives you an impression of the measurement uncertainty of the AC signal. And in this case, a non-sinusoidal rectangular AC signal. So this is a really nice tool, which I wanted to show at the end after a lot of theory that we also use practical measurement circuits to verify our analysis. And now I almost finished. I want to give you a short summary. So at the beginning, we discussed the major challenges in measurements on the powertrain. We saw that we have a lot of different physical quantities and also bus signals, communication signals, which should all be stored time synchronous in order to do some further analysis. Then, depending on the application, we need, of course, the cycle-based analysis, but also instantaneous values in order to investigate balancing processes and all those things. And what is not stated here, but what I explained is that we have a more or less new functionality. It's not part of standard perception so far, but you can use it with perception, and it's the highly dynamic power analysis and RMS calculation. And all those measurements all contain measurement uncertainty, and it's of course useful to minimize that. We saw that on the electric vehicle example, that the minimization of measurement uncertainty in the measurands allows a higher range specification. And it is quite easy for DC quantities and sinusoidal quantities, but it gets a real challenge if we talk about highly dynamic signals and arbitrary waveforms. And but also for this, I presented approach based on the discrete averaging, which is implemented in the measurement system. And at the end, you saw the hardware-based circuit, measurement circuit, which can be used to verify the analytical calculations. Now I want to show you the list of references. You can go read through that later on, I would say, and I thank you for your attention. Thanks for joining. And I'm happy to answer your questions. Thank you.
Awesome. Thank you so much, Alex. Now, if you have any questions, please type them into the WebEx Q&A dialog. And another reminder that today's presentation will be emailed to all attendees. The webinar will also be posted on our website. And go ahead, I'll give you another second or two to fill out the Q&A box. Double check here. Alex, we have a question that came in. Considering all information given so far, is it possible to calculate the measurement uncertainty of a HBM power analyzer?
Yeah, good question. So I would say yes and no, both. So the measurement uncertainty, it can be calculated, of course, if you know the power analyzer. But what you need in addition to that is the environmental conditions. So this is a very suitable method if you know what sensors are used in the measurement chain and you have the data sheet information. This is what I think the question means. Then you can do the measurement uncertainty calculation if you have, in addition, the environmental conditions. That's always important because measurement uncertainty is not only a characteristic of the measurement equipment. It is related to the measurement value because it is influenced by the measurement process, environmental conditions, and so on.
Okay, great. Thank you. And I have one other question here. You mentioned dynamic power calculation. Is it possible to calculate the MU for this?
Yes, that's also possible. That's related to the fact that we do this general measurement uncertainty estimation based on the discrete averaging, which means we have a number of n samples, and this number of samples is not restricted to a fixed time window. This can be the fundamental cycle, it can be the switching cycle, or it can be a time cycle which is independent from any electrical cycles. So this is a nice feature of this method, that it is applicable to any averaging process.
Okay, great. I think that wraps up all of the questions. No, there wasn't many, but Alex, if you'd like to switch to the next slide, if you have any additional questions that you would like to ask Alex himself, his information is here, alexander.stock@hbkworld.com. It looks like one last question came in just as I was saying that, Alex. How to calculate the number of cycles to average in order to minimize measurement noise?
Yeah. So the problem is the longer the better, I would say, if you can ensure that you are still in the same steady state operating point. And of course, what you also lose is dynamic in measurements. So as you saw from the slides before, I think I can explain that like this. The random errors are decreased by extending the averaging interval. But of course, if you do that, the update rate goes down. So it depends a bit on how often you need the information. And of course, if you have dynamic processes, long averaging leads to losing dynamic. That's the bad aspect.
Awesome. Hope that answered your question. If there are no other questions, I think we can end. So on behalf of Alex and I, we thank you so much for joining us. We look forward to seeing you at our next webinar. Thank you, everyone.
Thank you.
Bye.
Goodbye.